Production and Problems in the ETO. I changed the title of this section because, unlike any other airplanes we've looked at so far, the P-38 is such a story of contradictions. It was a highly successful aircraft that produced many aces and shot down more Japanese aircraft than any other. Versus, it was a widowmaker with all kinds of flying problems that took years to solve. It was a highly adaptable aircraft that was used in just about every role that one could imagine an airplane to do. Versus, it was a troublesome, uncomfortable airplane to fly, and if you didn't fly it just right, it would kill you. All of the previous statements are kind of true, and if you only heard the bad, you'd wonder why this aircraft wasn't cancelled long before. Let's take a look. One of the first problems with the P-38 was concerning it going into production at all. Lockheed was building Venturas, Harpoons, Lodestars, and Hudsons, and working on the Constellation when it started building the first 13 YP-38s, and it was struggling. The company was working on sorting out mass production problems when another problem reappeared, or I guess it never really went away. Let me describe to you this problem and how terrifying it must have been. Imagine you're tooling around in a P-38 at around 30,000 feet. It's a sweet airplane, and you're feeling like the bee's knees. It's a fast airplane, and you're a fighter pilot, so of course, you want to fly as fast as you can. You push the nose down and open the throttle. You glance down at the airspeed indicator gauge, and it's at about 320 miles per hour, and then something happens. You feel severe buffeting, and the airplane's tail begins to shake. Is it turbulence? A problem with the airplane controls? You try to raise the nose to reduce the airspeed, just as you've done with every airplane that you ever flown since you learned in a fabric-covered biplane. But this airplane won't have it. It continues to shake and seems to have a suicidal mind of its own as it shoves its own nose down. No matter how hard you pull, the controls are frozen and soon you are going down close to vertical. Yes, you had been at 30,000 feet, but now the altimeter is unwinding and the airplane seems determined to dive into the center of the earth. What do? Do you bail out? Do you keep trying to regain control? It's hard to regain control when you don't know what is actually wrong. Some did jump out. Some dove straight into the ground. One way out was to use the elevator trim to trim the nose up, and when the airplane dove into thicker air, the nose would lift, but ever so slowly. What made this problem so difficult to solve was that it was actually two problems happening at the same time with similar symptoms. The first was the previously mentioned tail flutter. This was solved by installing fairings, or fillets, where the wing meets the fuselage. This smoothed the airflow. They also installed counterweights on the elevator and tinkered with the angle of incidence on the horizontal stabilizer. This is the angle at which the tail plane was mounted on the aircraft. But the out-of-control diving kept happening. It would start happening at 425 miles per hour and would become deadly serious at 500 miles per hour. Now, if you don't know that you are dealing with two problems, you will probably continue trying to fix the first one, even though it isn't the thing that was killing pilots. So Lockheed and the Army continued to try to solve the flutter problem. They tried installing some spring-loaded servo tabs on the elevator trailing edge. These would kick in to try to aid the pilot when control yoke forces rose above 30 pounds force. On the 4th of November 1941, test pilot Ralph Verdon was given the job of testing out the new devices. And the test ended with the YP-38 going into a steep dive followed by a high G pullout, with the tail unit of the aircraft coming off at about 3,500 feet. Verdon was killed. They tried skinning the tail with thicker aluminum. they tried placing external mass balances above and below the elevator. Nothing worked. Even as P-38s were being delivered to combat units and were flying actual missions, the best solution that Lockheed and the Army could come up with was telling P-38 pilots, "Don't dive." It didn't take German pilots long to figure out that if they were tangling with P-38s and wanted to break away, all they had to do was perform a split S and head for the deck. The early P-38s were unable to pursue. And these weren't the only problems. As P-38s began arriving in Europe, serious engine issues began making themselves known. The first was more of a technique training issue. Most fighter pilots were being trained on single-engine aircraft, and the transition to the P-38 might be adequate, or more likely, rushed and lacking. If these pilots suffered an engine failure on takeoff, there was a good chance that they would do the wrong thing. Back in single-engine fighters, there's not a whole lot to do if you lose the engine on takeoff. You're shutting things down to hopefully prevent fire and stopping on the runway, or straight ahead into whatever is in front of the runway. With the P-38, if the pilot continued with full power on the good engine, the thrust from the good side and the drag from the bad side would yaw the aircraft over and flip it on its back. The technique that was finally developed was to pull back power on the good engine, feather the dead engine, trim the aircraft, and then gradually advance power on the good engine. That's a lot to do, and counterintuitive when you're low to the ground and just want to get up. Better training gradually improved this. Another massive problem boiled down to temperature. Smarter and more technical people than I might quibble about the details that I'm about to give, but let's just simplify it for the ease of understanding. Engines have a temperature range at which they operate properly, and features are built into the engines to keep the temperatures around there. The Allison engines did not tolerate heat very well. If things got too hot, the gasoline being sprayed into the engine might detonate or explode early, and this was bad. Detonation was detrimental to the pistons, rods, and crankshafts, and in very short order, a detonating engine might tear itself apart. So the engine systems were designed with many features to aggressively keep the temperature down. Oil coolers, intercoolers, radiators, etc. These worked well in balance at low to medium levels in the United States of America. Take them up to the freezing temperatures of 30,000 feet up over Europe, and these cooling systems were just too aggressive. The intercoolers in the turbos cooled down the fuel so much that the lead separated from the fuel, lowering the octane and resulting in fouled plugs, thrown rods, and swallowed valves. Radiators could lower the engine temps below normal operating minimums. Oil coolers could congeal the oil to a sludge. All of these could cause engine failures, and the best that could be said was that at least the P-38 usually had another one to get you home with. Other temperature problems were with the pilot, which is another thing that only operates well between certain temperatures. With single-engine fighters, it is relatively easy to duct some heat back to the pilot in cold temperatures, and even some just comes back through the firewall into the cabin on its own. With the engines out on the wings, it is very difficult to get heat back into the cockpit, and the heaters just weren't moving the heat from the engines to the cockpit. The pilots were cold, and at best they were uncomfortable. At worst, they were getting frostbite on their hands and feet. Also, the windscreen would ice up, and so the pilots couldn't see. And if you can't see, you can't fight. And you didn't even have the option of a power dive away, because that other problem wasn't solved yet either. So now that we've laid out all the problems, let's see how they were dealt with in operational history.